Hi everyone, so today I would like to continue with a new chapter which is topic 6, rotation of rigid body. In this chapter actually you can divide into 4 main subtopics. Okay, we have rotational kinematics, equilibrium of uniform rigid body, rotational dynamics, and conservation of angular momentum. Okay, so but for today we focus on this one, 6.1 only, which is about rotational kinematics. Okay, in 6.1, you can divide into 3 parts. You need to know about a little bit about definition and how to use, analyze parameters, and lastly, how to solve problem related to rotational motion. I think some of these symbols you already used in previous chapter, like theta, omega, right? And then I think previously you already learned about AC and so on. Okay, so it's very similar, you just add a few more. So first of all, what is rotational of rigid body? Rotational motion is about motion about fixed axis passing through the body as the body rotates. All points on the body move in circular path. So this one actually I took from your lecture notes. So rotational motion, you can imagine object rotates about this axis of rotation is what we call rotational motion. So rigid body means the object has a definite shape. Okay, it doesn't change. It's not like a gas or something. So those objects is like a solid. Okay, the particles composing it stay in fixed position relative to one another, so it doesn't change throughout the process. It is some of the example for rotation. We have a ball rolling down a ramp. Okay, this is the ball rolling down, so the motion here, it makes a rotational motion. Then a baseball bat in the air, and then a yo-yo up and down, so as it goes down and up, it undergoes a rotational motion as well. Okay, first of all, I would like to show you that there's a very it's very similar in terms of linear and rotation. It's just that the symbol that we use is a bit different. Okay, example, in linear motion we have displacement, we use a symbol S, velocity we use a symbol V, and acceleration we use a symbol A. Okay, but in rotational motion, displacement we use a symbol theta. This is what we call angular displacement. Okay, now velocity we have omega, which is what we call angular velocity, and lastly we have alpha, which is what we call angular acceleration. So this is basically angular displacement, angular velocity, and angular acceleration. Okay, and that's the relation between S and theta. Example here, S is equals to R theta. Okay, V is equals to R omega, A is equals to R alpha. So basically you can convert between linear and angular by simply multiplying with R here, right? R theta is equals to S, R omega is equals to V, and R alpha equals to A. Okay, and previously you already learned about centripetal acceleration. Okay, AC is equals to V squared over R. Okay, just use the same formula where V is equals to R omega, so R squared omega squared over R. This one you get R omega squared. So you can write AC in terms of V and in terms of omega. Okay, if you're not sure about the term that we use like angular displacement, angular velocity, or angular acceleration, you can always refer to the unit that they use. Okay, so example, as we use the unit meter, right? So this one is basically meter per second for velocity, and this one becomes meter per second square. Okay, similarly we have for angular displacement, we use angle, which is radian. SI unit for angle is radian, and this one becomes radian per second. So again, you can see it's very similar to the velocity here. Okay, this one meter per second, this one radian per second, and this one is radian per second square. Okay, I just copy those unit. I just want to write it over here. Radian per second, radian per second square. So alternatively, if not in SI unit, you can write angle there in terms of revolution or degree, but normally we seldomly use degree. Instead, sometimes you might use revolution. Okay, so I just write it down over here. Alternative to radian is revolution. Okay, this one is SI unit, another one is not SI unit. Okay, so one revolution is basically one complete cycle. I mean one complete circle lah, which is equivalent to 2 pi radian. Again, remember that this one is not SI unit. So example, if I have a circle, so theta there represent this part, the angle between two fixed points. Okay, this one is from the definition itself. So angle undergoes from fixed reference line, that one is your theta. So let's say this is point A and point B. So the distance in terms of angle or angular displacement is the theta itself. So this distance here, normally you write in terms of radian. Okay, but if it makes complete circle like from point A to point A, that one is basically one complete circle. So that one is actually one revolution. So I can write it down over here, maybe from A to A. This is what we call one revolution, which is equivalent to 2 pi radian. Okay, or 360 degrees lah. And then we have omega, instantaneous omega and average omega. So omega stands for angular velocity. Instantaneous means angular velocity at a specific position or at particular time. Okay, we only have that one particular value. And then omega average is basically rate of change angular displacement. In terms of formula, there's a slight difference. For instantaneous, this one becomes d s over dt. Sorry, if linear it is ds over dt, but this one is angular, so it becomes d theta over dt. Okay, and then omega average is basically total change in theta divided by total change in time. Okay, so you need to have final theta minus initial theta divided by total time. So it's slightly different in terms of formula, and how to use this formula is very similar to topic 2. Okay, you have ds over dt and delta s over delta t. And for instantaneous is very similar. This one becomes the omega over dt, and this one is basically delta omega over delta t. So that's the difference between average and instantaneous. Okay, but most importantly, if we are talking about one complete circle, again, omega is very similar to velocity, right? Just that this one in terms of angular velocity. So previously v is basically delta s over delta t, change in displacement over change in time. So if you are talking about angular velocity, change in displacement is basically delta theta, change in angular displacement divided by change in time. And if you are talking about one complete cycle, like these cases over here on the right here, right? So delta theta is simply 2 pi. So I can write down my formula, omega becomes 2 pi, and the time taken for one complete cycle start from A to A, right? So the time taken is 1 period. Okay, one complete cycle, the time taken is period. So you have to differentiate between small t and capital T. There's a difference. So capital T is for period, small t is for time. And this one, since 1 over period is equals to frequency, you can also write this formula as 2 pi f. Okay, this is a very important formula. You might be using this formula a lot. Okay, back to this one. Again, if in SI unit we have radian per second, if not in SI unit we have alternative, maybe we can use RPM. Okay, RPM stand for revolution per minute. So in 1 minute, how many revolution does the object makes? Okay, example 5 RPM means 1 minute 5 revolution. So you need to be able to convert units here. So example, if they give you in RPM, you have to convert to radian per second. If they give you in revolution, you need to be able to convert to radian. Okay, remember the SI unit for theta is radian, omega is radian per second, and alpha is radian per second squared. Okay, and then if you guys still remember, in topic 2 we have 4 linear equation. Okay, this one are the formulas equation, and similarly we have 4 in rotational motion. Okay, it's just that you have to change the symbol from linear to rotation. So previously we have V, now we have omega, so velocity becomes omega. So you can see we have 2 omega. One is for the final angular velocity, another one is initial angular velocity. The initial one we represent with omega naught. Okay, A is basically alpha, and the last one is time. Time doesn't change, no? So the equation becomes omega equals to omega naught plus alpha t. Okay, for second equation, S now becomes angular displacement, which is theta. U is initial angular velocity, omega naught, and A is basically alpha, that one is angular acceleration. So the equation becomes theta omega naught t plus half alpha t squared. We now refer to the equation 3. Try to write down the equation for rotational. V square becomes omega square, U square becomes omega naught square, 2A becomes alpha, S becomes theta. And the last one, as displacement is theta equals to half, U is omega naught plus omega t. I think that's it that you guys need to know for the first subtopic. Okay, continue to the next video for some example.